Good morning. Characteristic polynomial is what? Less than 2 weeks away from the mid-semester test, we should start accelerating. Especially if those reactions, the reactions of few of you were indicative of the overall success. We still don't know until we get the mark. But some people are really unhappy. If all of you are unhappy, then, well, I can do so much, but it's really up to you to improve. Okay. You don't remember, I did mention only towards the end of the last class when most of you were looking for the nearest exit, as if there was an emergency. If you don't remember, okay, try. That is a terminology you will, or you should, adopt. A transfer function is normally given as a ratio of two polynomials, numerator and the denominator. And it is the denominator that we call characteristic polynomial, because it is the denominator of the transfer function that determines the nature of the output, the nature of the response of the system. When we equate the characteristic polynomial with 0, we get characteristic equation. So characteristic polynomial equal to 0 gives us characteristic equation. When we solve the characteristic equation, we get roots of the characteristic polynomial. Roots of the characteristic polynomial will enable us to factorize the denominator. If we are lucky to have all roots real. If some of them are not real, then we'll have s squared plus 2 psi 1 omega n1 s plus omega n1 squared, s squared plus 2 psi 2 omega n2 s plus omega n2 squared, and so on. The point I'm trying to make here is that when you factorize any polynomial, in our case, the characteristic polynomial, you will end up with a number of first or second order polynomials. Any higher order polynomial, that means you haven't completed the factorization. Third order can be factorized further. Fourth order definitely can be factorized further. So once you complete the factorization, you will end up only with either first or second order polynomials. That means that any high order system can be regarded as a combination of first and second order systems. And that's why the lecture today, or the lecture we just started on Tuesday, deals only with first and second order systems. because we assume that higher order systems, you can deduce how higher order systems will behave if you know well how first or second order systems behave. Okay. Is this clear? Does this make sense, should I say? Because if it's not clear, it should be in an hour or less. So that's effectively what we said towards the end of the Tuesday's lecture. So you have a system. The system has a transfer function. The denominator of the transfer function is what we call characteristic polynomial. When it is equal to 0, we get the characteristic equation. Characteristic equation helps us find the roots. Roots help us factorize the denominator. And then if you remember partial fractions, we were talking about that, you can actually, once you factorize, that's why I didn't write on that piece of paper, when we factorize the denominator, we can actually break this transfer function into a sum of first or second order transfer functions. Okay. So we are going to study first and second order systems in a very practical way. We are going to apply 4 different inputs and see what outputs they are going to produce. And those inputs will be unit impulse, unit step, unit ramp, and unit cosine. So all of them unit because we want to keep it simple. The magnitude or amplitude of each function will be 1. And we will start with the first order system. So first order system has this form, k over s plus a. This would be a normalized form. And we will apply all 4 inputs we mentioned earlier. So first, let's apply a unit impulse. So you have a first order system, and your input is a unit impulse. What is the output? Well, first of all, in the S-domain, output equals transfer function times input in the S-domain. A unit impulse in the S-domain will be 1. So the output is k over s plus a. Output in the time domain is the inverse Laplace transform of the same thing. And if you check the tables, this is an example we had a few times so far. It's actually case 6, apart from you have 1, not k, up here. So it's k times e to the minus at. So it is k times e to the minus at. A very simple function to visualize, to present graphically. As time goes from 0 to infinity, you have an exponential decay because this argument is negative. So start when time is 0, the value of y of t is k, and then as time approaches infinity, the function approaches 0. The only important thing is after 1 over a seconds, after the time constant has passed, the value of the output will change by 63% of the maximum value, which is k in this case. Otherwise, it's a monotonously decreasing function, exponentially decreasing function. Okay. That should not be too difficult. A unit step input. Same transfer function, but unit step input. The output will be inverse Laplace transform of k over s plus a. Quick look at the tables. Here it is, case 14, apart from k missing, obviously, over here. So it's case 14. Apply this case back to our problem. So we have k over a into 1 minus e to the minus at. Again, we had this function earlier when we were actually talking about the meaning of the time constant. So this function starts from 0, because when time equals to 0, e to the power 0 is 1. 1 minus 1 is 0. When time is infinity, then this will be 0. So y of t will be equal to k over a. So it is k over a is a constant, and our response, our output, is exponentially, or asymptotically, if you want to call it, approaching k over a. And when 1 over a, when the time constant is reached, when time equals 1 over a, the value of the transfer function, the value of the output will change by 63% of the maximum value, which is, in this case, k over a. Okay. So this is, again, this shouldn't be anything new to you. I don't think we've had this example so far. So when you have a unit ramp applied as the input to the same system, then you have k over s plus a times 1 over s squared. Output will be the inverse Laplace transform of that. And we can still rely on our tables. Here's our case, 19. 1 over s squared s plus a. Again, k is missing in the numerator. This is the time domain. So y of t equals to k over a squared into e to the minus at, exponential part, plus another ramp function, at and minus 1, a constant. So if you want to sketch this one, where do we start? We can start with the asymptote first. So let's sketch the asymptote. This part, at times k over a squared, will be actually k over a. So it is this line here, k over a times t. Minus 1 times k over a squared. That means that that line needs to be translated downwards by k over a squared. So this is the asymptote now. This is our asymptote. And because of this exponential term here, we actually have finally our response looking like this. Starting from 0 and then asymptotically approaching the straight line. So at infinity, the output will be a straight line as well as the input. We applied an input to be a ramp function, a straight line. The output, after a certain period of time, will become a straight line again. The only difference is that the slope here is not 1. It's not 45 degrees. Here it is. So this line is 45 degrees to the x-axis, or time axis. But the output ramp will not be. Now, I think, before we move to the fourth case, that now you can, I hope you can notice that each of these responses or outputs can be divided into a steady state part and transient part. So in this particular case, this is a transient part of the response. Why transient? Because after a certain period of time, it becomes irrelevant. It becomes very small, very close to 0. As opposed to other terms here that are relevant throughout the time period we are observing. So this would be a steady state part of the response. So eventually, this is going to be your output. But it takes a while. How long it takes, well, depends on the time constant, 1 over a. So if you apply that logic back to the previous cases, this is the transient part, this exponential. Again, because you have e to the minus at, where a is a positive number and time is positive anyway. And this is the steady state part, or actually k over a times 1. Because it is a constant, we call it steady state value as well. So in this case, our response will reach a steady state value after a certain transient process. Back here, the response is completely transient. So the steady state part is 0. There is no steady state part. So after this transient process, the output will be 0. Okay. And this will be very important to understand the next example, as well as second-order systems a bit later. Okay, a cosine. So let's apply a cosine unit cosine function. By unit, we mean unit amplitude, not unit frequency. So frequency is omega. Same system, cosine input. Did I say output a bit earlier? Cosine input. Output will be equal to the product between the transfer function and the input. In the time domain, the output will be equal to the inverse Laplace transform of that product. This case does not exist in the tables, so you will have to apply partial fractions, which you all know how to do. And once you finish that process, you will find two parts of your output. Again, one is transient. This exponential will be multiplied by a constant. You see that everything here is constant. K and A are parameters from the transfer function. Omega is the frequency of the input cosine function. So everything is constant times exponential. Exponential has a negative argument. So this is a transient part of the response. This is a steady state part because there is nothing exponential here. So you have this cosine, you have this periodic function. And the amplitude is constant. Again, K, A, and omega. They are all constant. What that means, once again, that after this transient process expires, becomes irrelevant, you end up with a constant periodic motion, which is effectively what you had as the input in the first place. So you apply a cosine, you get a cosine. Now you see what changed between the input and the output is the amplitude. The input amplitude is 1, the output amplitude is not 1, a different constant. And you also have this phase shift. So the output is shifted by phi relative to the input. What didn't change is frequency. So the frequency of the input and the frequency of the output will be the same. And that's, if you remember our first lecture, that is an important property of a linear system, that the frequency will not change. Amplitude may, phase may change, frequency can't change. This plot, or this sketch should I say, shows the relationship between the input and the output after the transient process becomes irrelevant, when e to the minus at becomes so small that we can ignore it. And that's why we say this is not 0. So this is not really 0. This is just a part of the recorded input and the output after the transient process has gone. So this is the input, amplitude 1. So it's a cosine function with a constant amplitude. This is the output here. Amplitude is what we have here, K over A over square root of 1 minus omega over A squared. That is the amplitude of the output. The frequency, and therefore the period, or this is half period, is pi over omega. It will be the same for the input as well. So frequency did not change. Therefore, the period did not change. But the phase shift, or expressed as a time shift or time delay, will be phi over omega. Okay. So again, transient and steady state part. In case, because every year I get questions, maybe I should change this particular part of the lecture a little bit, but just to explain, I'll give you an idea what the actual output is like, full output. So first take that exponential part. Like this. And on top of that, you add the cosine. So superposition of two components of the output, transient and steady state. So our cosine is going to oscillate about this exponential. So initially, it is a cosine, but the neutral value of the cosine is this exponential. Somewhere here is what we are showing in our sketch in lecture notes. We decided that exponential is not relevant anymore. So this is not zero. This thing here. Any questions? So we decided to observe our output and compare it with input, just to see how they relate to each other. So we can see how the system, first order system, changes a signal. So you apply cosine as input. How different is the output relative to the input? Well, there will be difference in amplitude. There will be difference in phase. Any questions, guys? So in set 5, the first 4 examples actually cover these 4 cases. First order system with an impulse, step, ramp, and cosine. Okay, second order system is a more complicated case, because depending on the values of the coefficients in the denominator, we may or may not be able to factorize this characteristic polynomial. So we'll cover 4 cases. 4 cases. One is case 1, when we have 2 real roots, 2 real and different roots. So we can factorize this polynomial, so we get s plus alpha, s plus beta. That is possible if psi is greater than 1. Damping ratio is greater than 1. This system is called overdamped system. Please adopt this terminology, new terminology. The system is called overdamped if the damping ratio is greater than 1, or the roots are real and different. Case 2, if our roots are still real but identical. That will happen if the damping ratio is exactly 1. So when damping ratio is 1, we get 2 real identical roots of the characteristic polynomial. This system is called critically damped. Case 3, if we don't have any real roots, so the roots are two complex conjugate numbers, a pair of complex conjugate numbers. This case is called underdamped because the damping ratio will be less than 1, still greater than 0. Okay, complex conjugate roots. Now you can probably realize why this case is called critically damped, because it is just a special case between overdamped and underdamped. So a critical case. And finally, if the damping ratio is set to be 0, this system is called undamped. And the roots will be two imaginary numbers without real parts. The real parts will be 0. Okay, now that's new terminology for you. And it's all based on something you kind of know, and that's the roots of a second-order polynomial. And something that is also new to you, the value or values of the damping ratio. Okay, which again now answers some of the questions I was asked earlier. When we are doing inverse Laplace of this case, why don't we use the case when we can complete the square? Why do we use this case? Now I think it's getting clearer, because damping ratio is very important in defining the system. So I want to keep psi visible. Yeah, maybe if I go back to, I think those were cases 20 and 22. Yeah. This system, the case 20 and case 22, they're actually the same case. It is just different coefficients that we use. So in case 22, psi and omega n are preserved, the coefficients that have meaning to us. A and omega don't have much meaning in our case. Although you can see that this looks much simpler. But it is actually the same thing. Okay, now we have defined all four, not all, there are more. There are cases with psi being negative, between 0 and -1, and -1 to -infinity or whatever. But we will leave those cases out of this course. So we define 4 cases of different damping. And we already said we'll apply 4 different inputs. However, 4 different cases times 4 different inputs, that's 16 different combinations. We can't do everything. So we'll show some typical combinations and leave to you to just deduce what other combinations would yield as the output. However, we'll cover all 4 when the input is a unit impulse. Okay. So unit impulse applied as an input to an overdamped system, psi greater than 1. Okay. Then you're multiplying this transfer function by 1, and then looking for inverse Laplace transform. That's where tables are still helpful. And that would be case 15. Okay, apart from k missing here. I don't think I should keep pointing that out. And it's not A and B, it's alpha and beta. So the output will be equal to a constant times a difference of 2 exponential terms. Those exponential terms correspond to the roots of the denominator, alpha and beta. They are both decaying. They both have negative arguments. So the function will look like this. Function starts from 0, because when time is 0, you have 1 minus 1 is 0. And the steady state value is 0 as well, because when time is infinity, this is 0 and this is 0 as well. But in between you have this peak because the rate of decay is not the same, because alpha is different from beta. So it is not case 2 that they are equal. Alpha is different than beta, so you will have a peak. So you apply an impulse to a second-order system, and the output looks like a stretched impulse as well, just a bit slower. It doesn't jump up immediately. It doesn't jump down immediately. It actually follows this exponential curve until it gets back to 0. Okay. A critically damped system, an impulse input. Okay. So this transfer function times 1 it is case 7. T times e to the minus at. Over here, it's kt e to the minus gamma t. Try to analyze this function a little bit, and you will have something like this. So another function that starts from 0, reaches a peak, and then exponentially approaches 0. The difference between this one and the previous one is the peak is a bit higher and more narrow, and the exponential part decays much faster. Apart from that, seemingly they are the same or very similar. But critical damping is the fastest case of exponential response. So this decays faster than this. Under damped system, the damping ratio is less than 1, greater than 0. Oh, sorry, yeah? Gamma is just the other way we wrote the transfer function. So we don't mix with alpha and beta from the previous case or omega from the following case. So gamma is the root. Okay. So this case, when damping ratio is equal to 1, means that the roots are real and equal. So gamma is one of those real and equal roots. So again, gamma here is the root of the denominator the same way as alpha and beta were two real but different roots of the overdamped system. Yeah. Okay, any other question? Okay. Underdamped system. So damping ratio less than 1, greater than 0. Impulse, unit impulse is still our input. So this transfer function times 1, let's find the inverse Laplace transform. Did we say 22 earlier? Case 22, which is this one. Okay? So that means in the time domain, we'll have a constant, we'll have a decaying exponential function multiplying a sinusoidal function. Okay, constant, decaying exponential, and a sine function. Well, that means that we have a sine, but the amplitude is not constant. The amplitude is decaying towards 0. So the first amplitude will be the biggest, and then the following amplitudes will be smaller and smaller until they become 0. Yeah. Okay. So now this is the first time we see something strange, that the output will oscillate, although the input is not an oscillatory function. The input is an impulse. The output is oscillatory. But the oscillations are damped. An example, think of a pendulum, or think of a spring mass system. A pendulum, you push it, apply an impulse, just push it very quickly. It will swing, but it will eventually stop. It will swing with less and less amplitude. Or our spring mass damper. Push the mass down, not damper, sorry, spring mass, just spring mass. Push the mass down, and the mass will oscillate on the spring until it settles at 0 amplitude. That's what we have. So you don't have to apply an oscillatory input to get an oscillatory output. What you need is an underdamped system. The output will oscillate. But those will be damped oscillations. The amplitude will eventually become 0. And finally, if the damping ratio is 0, so we have this case 4 here, multiplied by 1, find the inverse Laplace transform. And I don't remember really where to look now. Okay, here we are. So the numerator is s squared plus omega squared. Denominator. The denominator is s squared plus omega squared. And as a result, we have sine omega t. Back here, we'll have this constant k omega times sine omega t. So now we have undamped oscillations. Therefore, the name undamped system. Our output oscillates forever with a constant amplitude, k over omega. Okay. So this is even worse than the previous one. Not only do we have an oscillatory output, but that output stays forever. And remember, the input was not oscillatory at all. The input was an impulse. How is this possible? Well, first of all, think about that pendulum I mentioned. You give it a flick, you apply an impulse, and it swings and eventually stops. Why does it stop? Why does it stop? Because of air resistance. Because of damping. It eventually stops. So this would be equivalent to having a pendulum in the outer space, in a vacuum. So you swing a pendulum and it keeps swinging forever. Constant amplitude. No resistance. Nothing to stop it. Which is, by the way, sorry for a digression, one of the problems with satellite technology or spaceships in general, and the particles that may hit them. Not only that those particles can generate damage, but even if it is such a small impact, one of the panels starts vibrating and the vibrations never stop because there is no damping. Okay. So this would be a case of an undamped system, or that would be the case. When you are in space, no damping. So oscillations last forever. Yeah, any questions on these impulse responses? Because we cover all 4 cases. Maybe just a little analogy with the first order system. Again, when you apply an impulse, there is no steady state part. Both terms here are transient. The steady state part is 0. So that's why our function eventually becomes 0. Here, this is the transient part. Again, exponential, but the argument is minus gamma t. Argument is negative. So again, steady state part is 0. Here, the whole expression is transient because of this exponential. Only here, you actually don't have anything transient. The steady state case is this sign. So in the case of an undamped system, there is nothing transient here. Okay, questions, comments? Okay, maybe just one more case before we commence our big tutorial. With a step input, we will only consider an underdamped system. So assuming that this polynomial here cannot be factorized, or that we have a pair of complex conjugate roots, or the damping ratio is between 0 and 1, excluding 0 and excluding 1. And if the input is a step, then you have this S term multiplying our original characteristic polynomial. The output is here. S times our second order underdamped polynomial. So we are going to have a sine function, and we are going to have an exponential, and we are going to have a constant as well. And of course, a phase shift. Okay, so we have a constant, and then we have minus a product of exponential and sine. Phi is defined as a function of the damping ratio. Okay, so let's see how this system behaves. Although we can sense there will be a steady state part and a transient part. This sine function can be expressed as sine of A plus B, and we probably know that that can be expanded as sine A cosine B plus cosine A sine B, where A is the first term here, omega n square root 1 minus psi squared times t, and B would be phi. So when we expand that, we have now still have this constant. Obviously, exponential is not changing, so we have sine, and we have a cosine. So we have three parts, three components of our output function. Let's use the superposition rule to see what the final form of this function is. Ignoring temporarily this, we say it is just a scaling factor. So only consider what's inside the brackets. So this is 1, obviously, very easy. The exponential part will have a decaying amplitude, as we had a few minutes before. So a sinusoidal function, but this exponential function will result in the amplitude being reduced to 0. This term here is a cosine, but also with a decaying amplitude. And it has a minus sign. So it will start from minus 1, and the amplitudes will decay to 0. If you combine these three, you are going to get a function that looks like this. So the output will oscillate, but not about 0. It will oscillate about a constant value. So it will settle eventually, but not at 0. It will settle at whatever the steady state value is. So let's check once again here. This whole part is the transient part, because it contains that exponential e to the minus something. This is the steady state part, and because it is a constant, it is also a steady state value, or final value. So eventually, our output will settle at k over omega squared. Or omega n squared probably would be better. Now, this particular combination, an underdamped system and a step input, deserves a completely new lecture. So next lecture, lecture 8, is only on this. So there are a number of parameters we want to examine in this particular case. Because that is probably the most usual case you're going to have, that the system is overdamped and you apply a step function as the input. Any questions? Yes? No, it is not for this system. It is not, first of all, because it is a second-order system. So in theory, it has two time constants. But because if you remember how we define the time constant, it is 1 over alpha and 1 over beta. So in this case, you still have two time constants. One time constant will be 1 over alpha, 1 over beta. If you didn't hear the question, I apologize. When I listened to my lectures, I realized that you can't hear the questions from the theater. So can we define time constants here? The answer is no. This system has no time constants because the roots are not real. So you can't find 1 over alpha, 1 over beta. That's why we need a new lecture for that, because we still want to have a measure of how quick the system is. If you remember, time constant tells us how quickly the system responds to the input. What do we do when we have an underdamped system that doesn't have a clearly defined time constants? Well, there are different parameters that we use for that. So, yeah, on Tuesday we'll talk about that, if we have time. If we finish this, obviously, we have to finish this first. So next lecture is on how we judge the behavior of an underdamped system in the absence of time constants. This is actually a very good question, because so far we were able to use the time constants to determine how fast this transient part is, how fast, how quickly it disappears. With the underdamped system, it's not that easy. Yeah. Any other questions? Okay, so now we can start our tutorials. The density is not that bad apart from this part. So again, I'm going to ask the third row to move somewhere else so we can reach everyone once the demonstrators come. So in this case, okay, you have two exponentials. But if one disappears very quickly, then the response will be dominated by the one that is longer. Okay? But it's not, you can't put the exact number on that, apart from, No, what they say, how strong is a chain? It's as strong as the weakest link in the chain. So if you're pulling the chain apart, it's the weakest link. So it doesn't matter, doesn't matter if one link is strong. The weakest one has to be strong. Or if you have a convoy of vehicles, so the speed of a convoy equals the speed of the slowest vehicle, not of the fastest.
So is there any other practical problems about two-time constant?
Oh, absolutely. Absolutely. You will see, once you start your solving of problems in the next tutorial, you will see. Yeah, there is, as I said, it's not always easy to analytically pinpoint, what happens, where this peak is or where, because it's not as simple as with a single, the first order system, single time constant. But you can see, you make, try 1 and 2 and try 1 and 10. And you will see that 1 and 10 is much slower. Not only that, try 1 and 2 and try 0.1 and 10. And you will see that the one that has 10 will be slower because the dominant one dominates the response. You can play with those.
Been shown several graphics.
That's first order.
What's the point of showing that?
That's the first order system.
Transient system.
What's the point? Maybe you should decide what's the point. I didn't know what to do, so I decided to show you this. Okay, no, just to show you, so you can draw some analogy. You apply an impulse, the system, the output gets back to zero. You apply a step, the output gets to a constant. You apply a ramp, the output gets to a ramp. You apply cosine, the output becomes a cosine. But there is always a transient period. It doesn't happen immediately.
So can we find the time constant for that system?
It's very hard. Well, no, you know the time constant, it's 1 over A. But it's 1 over A, for each system it's 1 over A. But you can't show it here that easy. Here it's very easy to show. 63% of the maximum, 63% of the maximum. But here, what is the maximum? Maximum is infinity. So it's not that easy.
So that's the system, and we create a partial fraction. So shouldn't there be two terms?
Oh, no. Well, you don't need partial fractions because you already have that in the table. You already have this.
Oh, yeah.
That's all. But you're right. In partial fraction, you have to take it twice. You can do it for practice. Probably, so what I assume that 1 will disappear. One will be 0. So 1 over s plus a will be 0, and 1 over 1 over s plus a squared will be still there. So that's my assumption. So we'll go in circles all the time.
I'm also thinking that's a homogeneous equation, differential equation, and then it has only one root, then the root is this root, and then theta is this root. That's what I'm thinking of theta.
Okay, I don't think we have it here.
So here is
What you can do also is use shift theorem. So if you have s plus a cubed, then just treat it as s over s cubed. And then apply. So this is so this is effectively 1 over s.
Yes.
Okay. 1 over s is just t. Sorry, 1 over s squared. This is 1 over s squared. So it's t. But then you have this shift by a, and then you multiply by a. Okay. So there are a few ways to answer that. So if it is s plus a, and then you to power or anything, just treat it as a shift.
In this case, what happens if a becomes less than 0?
What becomes less than 0? Sorry. What?
When a is smaller than 0.
Oh, that's a different thing. That means, okay, that's something that is coming. That is, the electorate is coming. That means that you have e to the plus at. That means that the amplitude is increasing. So transient becomes unstable. So the system is unstable. That's what we call that instability. The amplitude is getting bigger and bigger because S is a negative number.
And it doesn't matter what input is.
That's true. The system will be unstable. Yeah, you're going ahead a little bit. But that's true. Stability does not depend on the input, it depends on the system itself. So can I close this so I start to walk through the class? I got seconds.
Yeah, maybe like 1 second.
Ivan. Hey, Michael. Just don't want to log on while they're watching mine.
Oh, you mean the lecture recording?
No. They want the. I need to log on to show them the tutorial set.
Ah, right.
But while I'm logging on, I want the camera to be switched on.
It doesn't show your password anyway.
No, it shows my Z number, which, is, again, something I don't necessarily want to share with so many people.
Z number. I can't really do anything with just the Z number though.
I know, but it's half of what they need to hack my account. My Z number and my password. So 50% done.
So you did, what was it, set 5 today? Enough
Yeah,
to
but
set
only
five?
first order systems.
Okay.
Only first 4 examples. Where is the?
Because in today's shoot, I finished off set 4, I think the block diagram.
Okay, yeah. I'll send later today. I'll send instructions for next week. Okay, I'll wait. I have to remember to log off before I leave.
get some value of k.
So it doesn't matter if
No, no, it is just that you are not given the data yet, but the equation tells you that it's starting from some point A, so it could be say 4.5 or something, and it increases up to
the premise is just defined as
K and P.
A is the time constant.
A is not the time constant, your time constant is 1 upon n.
So what's A is
So like one A is not a variable, like it's a constant, but the time constant is 1 upon n. Because
I thought it was room controls here. Down here it's not, you know, but yeah. Up there it's getting a little bit. Thanks. You should have those examples ready.
do that or contact
Oh yeah, if you'd be awesome.
is my email. There is even
raises it. I spent like 5 minutes rubbing water every single day. First week I was using my hands.
It's good. It's nice sometimes on they say that they
Second week I was like, I upgraded to paper towels. Third week the eraser. Efficient eraser.
If we don't get bigger numbers next time, next Friday, then
because
I
there
think,
is a test.
because test is week 6, next Friday is week 5. Then, but they don't. They should know that, not you. Yeah. Then we are going to have big problems.
Okay.
This is really not good.
Bring it home. They all stopped working. So I'm like, we're out of luck in this one. The Nickton from where I used to work in Saturday. Every week I'd grab one after take it home, just take it home. So I just had like a stack of 20. They all went well. I mean, I don't work there anymore, so I don't want to work there. Guy kept paying late. I think some people are still like 2 months behind on their payment. Like it was okay for the first 2 years, and then they sold it off to some kid. Like you look dodgy from the get-go. Yeah. He's paying really late. I just don't like his face. It's not worth it. Well, it's easy work. I need my Saturdays. It's too stressful. So I want to work 6 hours a day. Drive around. And again, now I have too many free days. Mondays free, Thursdays free, Saturday and Sunday free. That was like 4 years ago. 4 years ago. 1, 2, 3. Regrets taking it. Should have taken 1, 2, 4. Yeah, I trained for that one. Physics was too hard. After high physics for me, I was like, nah, I'm out here, straight out here. But then, like, I look back at physics on me, like, that shit was easy. Like, I was strong as that. I just remember the fun. It was like, I just remember 3 capacitors in, like, parallel. Like, it's the easiest question I can do. I'll just young and naive. Last year, this year, then this year, last year. wanted to do something. Go ahead.
You can ask
I don't
Avery.
want to help. They have to ask me. Who's making money with minimum effort? That should be everyone's goal.
Yeah.
Is that a hand up?
So you drive from
I don't live in Wollongong.
something.
If I lived in Wollongong, I would have went to University of Wollongong. I live in Ingleburn.
It's further or near.
It's like halfway to Wollongong.
It's okay.
No, I didn't drive today. I only got 2 hours to sleep. I was like, and I need to prepare for the trip on the train. Save money. I realized that driving was too expensive. Oh, I always find parking. Parking's too expensive. Petrol.
Yes, it's great, but I have to transportation.
No, I just park further. I park like 1 kilometer that way, so it takes me 20 minutes to walk up to my biome.
You take this way, you need a.
I'm going on Tuesdays, right? I park all the way over there, so like, there's like 2 away from, so I walk all the way up to Samuels for my thesis, walk down to Webster for my vibration shoot, and then run back up to Matthews D for this course.
It is fun. No, let him do that.
Why today?
She charged you or something.
Let's go together.
Really?
How long does the cold virus live outside of you? How long does the cold virus live? It's circular. The circular. Explain the circular. Oh. Well, you didn't hurt it? Don't worry. I had obviously had a pretty bad cold. Why do you wash your hands after? You wanna go help him? Fine, feel okay then. So when came first week back, I got an infection. Well, the week before I came back, I took a rash and I always very much. So that was my first week, so just second week, I got like conjunctivitis and stuff like that.
Maybe they can manage to promote the problem.
Well, I would like to think that way. That word that they saw a little bit of sunshine after 2 weeks, and they just
And there is an issue regarding tennis. They are expecting this problem of the test to be very similar to the tutorial problem.
and that's what they are complaining. I mean, if you notice the discussions and also when they come to me, I don't know why. I mean, in the past they realize that tutorial sets are just a way of learning, not that we're going to test it on those examples. So, as I said, one of the first complaints that I got is you don't put H, capital H, on conversion factors. Oh, yes. So what?
I have this issue. Here, they are really expecting not for this course, but for every course to be treated like this.
So it's conversion power H, okay? And I didn't put it in the test. And they're complaining, well, it's not the same problem. Well, you should be happy, it's so similar. And I told them, well, expect a change. If I take the problem from the tutorial set, I will change it. It won't be 100% the same. But they somehow feel entitled to having exactly.
I mean, mean, their expectation is that they consider tutorial classes and find solutions and learn them.
At least my experience was not like that. This is the first year, so many of those expecting that. So that's something I have to emphasize.
Yeah, because for example, what the tutoring was asking for, the vibration is like the solution, the questions are typical. You find various what you can address, but dynamic is different. Every question is different from the other.
Okay. Oh, no, that's okay. I just want to have a quick look. That's all. Actually, to be honest, it's not you. It's you, it's the guy that you turn out. Because of him, I wrote that request. Well, I said, how many emails do you get about when the test is going to be? And then if you don't respond, well, that's you're not prepared. Don't worry, thanks very much. You see, constant angular velocity. Okay. But this is angular displacement.
projectile motion. Let's say 2 has a big number. How many big numbers? That's what it means. The limit has x. So you show him the limit. Now prove that the limit converges.
Okay, I'll give you several times so you can list the.
Keep going. Just keep going. How can the limit be zero?
You mean the linear?
Yeah.
The limit equals this.
Yeah, the limit equals but it never equals it. So what if he asked that? What if he asked?
No, you're right. Over infinity is equals.
Yeah, I really hate it when people write stuff like this. I refuse to use infinity as a number.
Yes.
That's good and
So
right.
it's like
That's right.
when they put infinity into time domain function, and I'm like, I have to write the limit as t goes to infinity. T. I have to write that.
Right.
Every time I see it in the answer square, it's like, oh, t of infinity. What is the steady state response? Zoran doesn't like anything. Right.